We know that both the silicon and germanium form 4 covalent bonds with neighboring atoms. When a trivalent dopant, say aluminum atom, is added to a silicon semiconductor crystal, the aluminum atom occupies the same position of a silicon atom in the crystal. A trivalent dopant atom forms covalent bonds with 3 neighboring silicon atoms. The dopant atom has no electron to share with the 4th neighboring silicon atom. Therefore, a hole is created in the lattice. Each trivalent dopant atom creates 1 hole in the crystal lattice of the semiconductor. At room temperature, some of the electrons break away from the bonds, giving rise to electron-hole pairs. And simultaneously, some of the free electrons recombine with the holes and reduce the number of intrinsically generated electrons. Therefore, the number of holes in a semiconductor doped with a trivalent dopant is larger than the number of free electrons. So the positively charged holes act as the majority charge carriers in such a semiconductor doped with a trivalent dopant. Such an extrinsic semiconductor is called a p-type extrinsic semiconductor. Despite the difference in the number of holes and electrons, the p-type semiconductor remains neutral. When a valence electron fills the hole generated by the dopant atom becomes negatively charged. Therefore, a dopant atom in a p-type semiconductor is called a negatively charged core or an acceptor impurity. A p-type semiconductor has an acceptor impurity band lying just above the valence band. Therefore, the valence electrons can leave the valence band by covering a much smaller energy gap as compared to an intrinsic semiconductor. The electrons can move to the acceptor impurity band even at room temperature to create holes in the lattice. This makes conductivity of a p-type semiconductor much better than an intrinsic semiconductor. Let's now see what happens when a pentavalent dopant, say a phosphorus atom, is added to an intrinsic silicon semiconductor crystal lattice. The dopant forms covalent bonds with 4 neighboring silicon atoms. The dopant atom still has 1 free electron. And therefore, each pentavalent dopant atom contributes 1 free electron to the crystal lattice of the semiconductor. So, the number of free electrons available for conduction by dopant atoms depends largely on the level of doping. If the amount of dopant is high, the number of free electrons increases. This number of free electrons contributed by the donor dopant is not dependent on the temperature of the semiconductor. But if the temperature increases, the number of electron-hole pair increases, further adding to the conductivity of the crystal. Therefore, in a semiconductor doped with a pentavalent dopant, the total number of conduction electrons is due to the free electrons contributed by the dopant atoms and those generated intrinsically. Due to increase in the number of free electrons, the rate of recombination of holes increases, effectively causing a decrease in the number of holes compared to the number of electrons available for conduction. So the number of electrons is much higher than the number of holes. The negatively charged free electrons are thus the majority carriers in such a semiconductor doped with a pentavalent dopant. Such an extrinsic semiconductor is called an N-type semiconductor. When a dopant atom gives up its electrons, it becomes positively charged. Therefore, a dopant atom in an N-type semiconductor is called a positively charged core or a donor impurity. The N-type semiconductor has a donor impurity band lying just below the conduction band. Therefore, electrons can jump from the conduction band by covering a smaller energy gap compared to an intrinsic semiconductor. This movement can happen even at room temperature.